Imagine a quiet, serene night shattered by a deafening explosion. The ground trembles beneath your feet, and a fiery plume of ash and smoke climbs miles into the sky. This was the reality in 1883, when Krakatoa erupted with a force so immense that it could be heard 3,000 miles away. Entire islands were obliterated, and the sky turned a haunting red for days. Yet, what's most chilling about Krakatoa's eruption isn't just its power, it's the suddenness. Could there be other volcanoes lying in wait, ready to unleash similar destruction without warning? What if I told you that the most dangerous volcanoes aren't the ones we see on postcards or in textbooks? The ones that truly pose a threat often hide in plain sight or deep beneath the ocean, cloaked in mystery. These geological wonders hold secrets that scientists are still striving to uncover, their unpredictability serving as a reminder of how little control humanity has over the Earth's immense power. Volcanoes are more than just mountains that erupt. They are living, breathing entities, shaping and reshaping the planet in ways both visible and unseen. Their potential for destruction is equaled only by their ability to fascinate us, drawing us into their fiery depths with stories, myths, and mysteries that have endured for centuries. The magnetism of volcanoes for millennia, volcanoes have captivated human imagination. In ancient mythology, they were often seen as the wrath of gods or gateways to the underworld. The Greeks believed Mount Etna was home to Hephaestus, the god of fire and metalworking. Hawaiians revered Pele, the goddess of volcanoes, who was said to control the fiery eruptions of Mauna Loa and Kilauea. These myths offered explanations for the incomprehensible power of these natural phenomena, blending fear with reverence. Beyond mythology, volcanoes have a tangible impact on civilizations. Their eruptions can create fertile lands that sustain agriculture for centuries, as seen in regions around Mount Vesuvius. Yet, they also have the capacity to wipe out entire cities, as Vesuvius demonstrated when it buried Pompeii under layers of ash in AD 79. This duality, the capacity to create and destroy, keeps us intrigued and vigilant. Even in modern times, volcanoes remain symbols of awe and terror. They challenge our scientific understanding, defy our ability to predict their behavior, and remind us of nature's raw, untamable power. From the majestic slopes of Mount Fuji to the hidden underwater volcanoes of the Pacific, they command our attention and fuel our desire to uncover their mysteries. The mysteries waiting to be unveiled in this journey, we'll dive into the world of volcanoes, uncovering secrets that lie beneath the Earth's crust. We'll explore eruptions so massive that they altered the course of history, delve into unexplained phenomena like volcanic lightning and mysterious sounds, and venture into the hidden chambers deep beneath the surface where molten rock churns. Along the way, we'll unravel the role volcanoes play in shaping our planet, their impact on the atmosphere, and how life rebounds in the wake of destruction. But perhaps the most intriguing question of all is what we don't know. Are there undiscovered supervolcanoes waiting to reveal themselves? Can we ever truly predict when a dormant volcano might awaken? And what are the implications for humanity if one of these geological giants were to erupt tomorrow? As we embark on this exploration, prepare to see volcanoes in a whole new light, not just as mountains that spew lava, but as complex systems intertwined with the Earth's history and future. The mysteries they hold could redefine how we understand our planet, its power, and our place within it. The science behind volcanoes. The birth of a volcano. Volcanoes are Earth's way of releasing pressure, a reminder that beneath the surface lies a molten world in constant motion. But how exactly do these fiery giants form? The answer begins deep within the Earth's crust, where tectonic plates slowly shift and collide. At the boundaries where these plates meet, immense heat and pressure build, melting rock into magma. In some areas, this molten rock rises through cracks in the crust, creating volcanoes along subduction zones, where one tectonic plate slides beneath another. This is why regions like the Pacific Ring of Fire, stretching from South America to Japan, are home to over 75% of the world's active volcanoes. Subduction is responsible for some of the most violent eruptions in history, as the descending plate melts and forces magma to the surface. Volcanoes also form in places where no tectonic boundary exists. These are called hotspots, anomalies where plumes of magma rise directly from the mantle. Hawaii, for example, sits atop a hotspot that has been active for millions of years, birthing islands one eruption at a time. Unlike subduction zones, hotspot volcanoes can appear in the middle of tectonic plates, far from plate boundaries. Rift zones are another breeding ground for volcanoes. As tectonic plates pull apart, magma seeps through the thinning crust, creating new land. Iceland's unique landscape owes its existence to this process, as the island straddles the mid-Atlantic ridge, a vast rift where the Eurasian and North American plates diverge. Whether born from subduction, rifting, or hotspots, all volcanoes share one thing in common: they are dynamic, evolving structures capable of reshaping entire landscapes in a matter of hours. Types of volcanoes and their distinct personalities. Not all volcanoes are created equal. Their shapes, sizes, and eruption styles vary dramatically depending on how they form and the type of magma they produce. Shield volcanoes are the gentle giants of the volcanic world. Their broad, sloping profiles are built by the slow flow of basaltic lava, which spreads across vast distances. Mauna Loa in Hawaii, the largest volcano on Earth, is a prime example. Its eruptions are effusive, meaning they produce rivers of lava rather than explosive blasts. These volcanoes can grow to enormous sizes, but their eruptions tend to be less destructive to human life. Stratovolcanoes, on the other hand, are far more dangerous. With their iconic conical shapes, these volcanoes are built from alternating layers of ash, lava, and rock. Mount Vesuvius in Italy is a classic stratovolcano, one that buried Pompeii in AD 79. Stratovolcanoes are known for their explosive eruptions, driven by thick, gas-rich magma that traps pressure until it violently bursts forth. Cinder cone volcanoes are the smallest and simplest. They form from explosive eruptions that spew fragments of rock and ash into the air, which then accumulate around the vent. These cones rarely exceed 300 meters in height and often erupt for brief periods before becoming dormant. Paricutin in Mexico famously emerged from a cornfield in 1943, growing into a full-fledged cinder cone within a year. Then there are the supervolcanoes, ticking time bombs beneath the Earth's crust. Yellowstone in the United States is the most famous example. Unlike typical volcanoes, supervolcanoes don't form towering peaks. Instead, they create massive calderas, depressions left behind after colossal eruptions. A supereruption can eject thousands of cubic kilometers of material, enough to blanket continents in ash and trigger global climate shifts. Each type of volcano carries its own risks and rewards. Some create fertile land that supports agriculture, while others threaten entire civilizations. Understanding these differences helps scientists predict how volcanoes will behave, providing valuable insight into the forces that shape our planet. The anatomy of an eruption. Volcanic eruptions are among the most awe-inspiring natural events, but what determines whether a volcano will erupt gently or with catastrophic force? The answer lies in the chemistry of the magma, the gases trapped within it, and the pathway it takes to the surface. Effusive eruptions, like those from shield volcanoes, occur when magma flows freely. This type of magma is low in silica, making it less viscous. As a result, gas escapes easily, and the lava can spread across the landscape without explosive violence. In contrast, explosive eruptions are driven by viscous, silica-rich magma. This thicker magma traps gas, allowing pressure to build until it erupts in a powerful blast. Stratovolcanoes are notorious for this type of activity, producing pyroclastic flows, avalanches of hot gas, ash, and volcanic rock that race down the slopes at terrifying speeds. The intensity of an eruption is influenced by the volume of gas dissolved in the magma. The more gas, the more explosive the eruption. Water vapor, carbon dioxide, and sulfur dioxide are the primary culprits, expanding rapidly as magma rises and decompresses. Another critical factor is the structure of the volcano's vent system. If the vent becomes blocked, pressure can build to dangerous levels. When the blockage finally gives way, the resulting eruption can be catastrophic. This was the case with Mount St. Helens in 1980, where a lateral blast obliterated the surrounding landscape. Volcanic eruptions, whether gentle or violent, are complex processes shaped by countless variables. Each eruption tells a story, a glimpse into the inner workings of our restless planet. The dangers of lava, ash, and pyroclastic flows. While lava flows are often the most visually striking aspect of a volcanic eruption, they are rarely the deadliest. Lava typically moves slowly enough for people to escape. However, it can bury homes, forests, and infrastructure, leaving a lasting mark on the landscape. Ash, on the other hand, poses a more insidious threat. During explosive eruptions, volcanic ash can be ejected high into the atmosphere, where it spreads over vast distances. Fine particles of ash can collapse roofs, contaminate water supplies, and disrupt air travel. When inhaled, volcanic ash can cause respiratory problems, posing a serious health risk to those living downwind of an eruption. Pyroclastic flows represent the most immediate and lethal hazard. These superheated clouds of gas, ash, and volcanic debris can reach temperatures of up to 1000 degrees Celsius and travel at speeds exceeding 700 kilometers per hour. Entire towns have been wiped out by pyroclastic flows in minutes, leaving behind nothing but scorched earth. Lahars, or volcanic mudflows, are another hidden danger. When volcanic ash mixes with rain or melting snow, it can form a dense slurry that rushes down river valleys, engulfing everything in its path. Lahars can occur long after an eruption has ended, catching communities by surprise. Understanding the different materials ejected during an eruption provides a clearer picture of the risks volcanoes pose. It's a reminder that while volcanoes can create stunning natural wonders, they also hold the power to reshape the world in ways both beautiful and destructive. Case studies: the world's most mysterious volcanoes, Mount Tambora, the eruption that changed the world in April of 1815, Mount Tambora, a seemingly ordinary volcano on the Indonesian island of Sumbawa, erupted with a force so immense that it remains the largest volcanic eruption in recorded history. The explosion was heard over 2,000 kilometers away, and the ash it spewed into the atmosphere circled the globe. Tambora's eruption was not just a regional disaster, it altered the course of global climate, transforming the following year into what became known as the year without a summer. At the heart of this colossal event was a series of explosive eruptions that released over 160 cubic kilometers of material. To put that in perspective, the eruption of Mount St. Helens in 1980 expelled only 1 cubic kilometer. The force of Tambora's blast ejected an ash column over 43 kilometers into the stratosphere, blocking sunlight and reducing global temperatures by as much as 3 degrees Celsius. This seemingly minor shift wreaked havoc on agricultural systems, triggering crop failures in North America and Europe. Famine swept across regions that had previously been lush and fertile, leading to widespread food shortages and social unrest. The eruption's immediate impact on local populations was catastrophic. Over 10,000 people were killed instantly, either buried beneath pyroclastic flows or crushed by falling ash. Entire villages were erased from existence. But the indirect death toll, driven by famine and disease in the following months, soared to nearly 100,000. Survivors fled to neighboring islands, only to find the surrounding seas blanketed in floating pumice and fish populations decimated by the ash-choked waters. One of the great mysteries surrounding Tambora is why it erupted with such unprecedented force. Scientists believe the volcano had been dormant for centuries before 1815, quietly accumulating magma beneath the surface. Over time, the magma chamber swelled, becoming rich in volatile gases. The immense pressure built slowly, and when the volcano finally gave way, the eruption was unlike anything humanity had witnessed in modern times. Despite its violent past, Mount Tambora remains active today, though on a much smaller scale. Its caldera, formed when the peak collapsed after the eruption, now measures over 6 kilometers wide. Within this depression lies a crater lake, a serene yet haunting reminder of the volcano's destructive power. The caldera walls bear the scars of previous eruptions, offering glimpses into the volcano's history for those willing to brave the trek to its summit. The lingering question remains: could Tambora erupt with similar force again? Volcanologists closely monitor the region, aware that the processes that led to the 1815 eruption could, in theory, reoccur. However, the likelihood of another super-eruption remains uncertain. While the Earth's internal processes are cyclical, the build-up required for an eruption of that magnitude takes centuries, if not millennia. For now, Tambora stands as both a monument to nature's ferocity and a testament to the delicate balance that governs life on Earth. Its legacy serves as a reminder that even the most remote volcanoes hold the potential to reshape the world in ways we may never fully anticipate. Krakatoa, the volcano that shook the world in August of 1883, the small volcanic island of Krakatoa, nestled between the islands of Sumatra and Java in Indonesia, erupted with such force that it became one of the most infamous volcanic events in human history. The explosion was so violent that it was heard over 3,000 miles away, as far as Australia and islands off the coast of Africa. This single event reshaped not only the physical landscape but also the understanding of volcanic power. Before the eruption, Krakatoa had shown signs of unrest, tremors and minor ash plumes had been recorded for months. However, nothing could have prepared the region for the devastation that followed. On August 26, a series of eruptions intensified, culminating in 4 massive explosions the following day. The loudest of these was so powerful that it ruptured the eardrums of sailors nearly 40 miles from the island. It remains the loudest sound ever recorded in history. The consequences of Krakatoa's eruption were catastrophic. Entire islands were obliterated by the blast, and the resulting tsunamis, some reaching heights of 40 meters, swept across coastal communities, killing more than 36,000 people. Villages were submerged, and entire populations were wiped out within minutes. In the aftermath, ships reported encountering vast fields of floating pumice, while skies were darkened by ash for weeks. Beyond the immediate destruction, Krakatoa's eruption had a profound impact on the global climate. The vast quantities of ash and sulfur dioxide injected into the atmosphere created vivid sunsets around the world and caused a noticeable drop in global temperatures. Scientists estimate that the Earth cooled by approximately 1.2 degrees Celsius in the year following the eruption. This climatic disruption, while less severe than Tambora's year without a summer, still contributed to crop failures and weather anomalies across the globe. Perhaps the most fascinating aspect of Krakatoa's legacy is Anak Krakatoa, the child of Krakatoa. In 1927, nearly 44 years after the original eruption, volcanic activity resumed beneath the ocean. Over the decades, a new island began to emerge, rising gradually from the sea. This island continues to grow, erupting periodically and serving as a living reminder of Krakatoa's enduring activity. Anak Krakatoa's eruptions, while smaller in scale, demonstrate that the volcanic system beneath the region remains active and volatile. The question that lingers in the minds of volcanologists and residents alike is whether Anak Krakatoa could one day unleash an eruption rivaling that of 1883. While the formation of Anak Krakatoa has relieved some pressure, the potential for future catastrophic events cannot be ruled out. In December 2018, Anak Krakatoa partially collapsed during an eruption, triggering a deadly tsunami that struck Indonesia's coastline, killing over 400 people. This event highlighted the unpredictable nature of the volcano and its capacity to disrupt lives even today. Krakatoa's story is far from over. The region's volcanic activity continues to shape the landscape and serves as a stark reminder of the immense power that lies beneath the Earth's surface. As Anak Krakatoa rises from the depths, the world watches, knowing that the forces responsible for one of history's most violent eruptions are still at play. Mount Vesuvius, the sleeping giant of Italy in the year AD 79, Mount Vesuvius unleashed one of the most infamous eruptions in history, burying the Roman cities of Pompeii and Herculaneum beneath a thick blanket of volcanic ash and pumice. What made this eruption so catastrophic was not just its intensity, but the eerie silence that preceded it. For years, the volcano had shown no obvious signs of danger, allowing the region's population to thrive along its fertile slopes. When Vesuvius finally erupted, it caught thousands by surprise, entombing entire cities in a matter of hours and preserving them as time capsules of Roman life. The eruption began with a violent explosion that propelled ash and volcanic debris miles into the sky, creating what Pliny the Younger, an eyewitness to the event, described as a pine tree of smoke. As the eruption progressed, pyroclastic flows, superheated clouds of gas and ash, raced down the volcano's flanks, engulfing Pompeii and suffocating its inhabitants. In Herculaneum, the intense heat carbonized wooden structures and left behind skeletons of those who had sought refuge along the coast. By the time the eruption ended, over 16,000 people had perished, and 2 cities had vanished beneath layers of volcanic material. What makes Mount Vesuvius so mysterious is the irregular pattern of its eruptions. After AD 79, the volcano continued to erupt periodically, with significant events recorded in 1631, 1872, and 1944. However, these eruptions pale in comparison to the devastation wrought in ancient times. Scientists have long puzzled over the gaps between Vesuvius's major eruptions. Unlike some volcanoes that erupt on a predictable schedule, Vesuvius operates on its own timeline, sometimes lying dormant for centuries before awakening with sudden fury. One theory suggests that the buildup of viscous magma beneath Vesuvius contributes to the unpredictable nature of its eruptions. As magma accumulates, gas becomes trapped, increasing the potential for explosive activity. The longer the volcano remains quiet, the greater the likelihood that its next eruption could be catastrophic. This cycle of dormancy followed by violent awakening mirrors what occurred in AD 79, raising concerns that Vesuvius could be overdue for another major eruption. Today, Vesuvius is considered one of the most dangerous volcanoes in the world, not just because of its eruptive history but due to the dense population living around its base. Over 3 million people reside in the shadow of the volcano, making Naples and the surrounding areas highly vulnerable to future eruptions. Despite advancements in volcanic monitoring, predicting exactly when Vesuvius will erupt remains a challenge. Seismic activity, gas emissions, and ground deformation are closely watched, but these signs often provide little more than a short warning window. The potential for another catastrophic eruption has led to ongoing evacuation plans and emergency preparedness drills. Yet, the allure of living near such a powerful force of nature continues to draw people to the region. The fertile volcanic soil supports lush vineyards and agriculture, a testament to the life-giving properties of the very force that once destroyed entire cities. Mount Vesuvius stands as a reminder of the delicate balance between creation and destruction. As it slumbers, the question lingers: when will the sleeping giant awaken once more? Yellowstone supervolcano, a colossal threat beneath the surface. Beneath the picturesque landscapes of Yellowstone National Park lies one of the most powerful volcanic systems on Earth, the Yellowstone supervolcano. Unlike the towering peaks of typical volcanoes, Yellowstone's volcanic nature is concealed beneath a sprawling caldera, a massive depression that stretches over 70 kilometers across. This caldera is the result of cataclysmic eruptions that occurred hundreds of thousands of years ago, the most recent of which happened approximately 640,000 years ago. That eruption ejected an estimated 1,000 cubic kilometers of volcanic material, covering large swaths of North America in ash and reshaping the continent's geography. What makes Yellowstone unique is the vast magma reservoir hidden beneath the surface. This reservoir feeds a dynamic geothermal system responsible for the park's famous geysers, hot springs, and bubbling mud pots. While these features attract millions of visitors each year, they are also signs of the immense power that lies dormant beneath the ground. Scientists estimate that the magma chamber contains enough molten rock to fill the Grand Canyon multiple times over. Despite its immense potential for destruction, Yellowstone's current activity is relatively calm. However, the supervolcano is constantly monitored by the Yellowstone Volcano Observatory, YVO, a collaboration between the U.S. Geological Survey, USGS, and other scientific agencies. By analyzing seismic activity, ground deformation, and gas emissions, scientists can track subtle changes in the magma chamber. The park experiences thousands of small earthquakes annually, most of which go unnoticed by visitors but provide valuable data about the movement of magma and tectonic shifts. One of the most pressing questions surrounding Yellowstone is whether it could erupt again with the same force as it did in the distant past. A supereruption on the scale of Yellowstone's previous events could potentially blanket much of the United States in ash, disrupt global climates, and trigger widespread agricultural collapse. Some models predict that the ash fall could extend as far as the East Coast, grounding flights and crippling transportation networks. The long-term climatic effects could lead to what's known as a volcanic winter, where sunlight is blocked by ash in the atmosphere, causing global temperatures to plummet. However, scientists caution that such an eruption is unlikely to occur anytime soon. Geological records suggest that supervolcanoes erupt on cycles that span hundreds of thousands of years, and there are currently no signs that Yellowstone is nearing another major eruption. In fact, the most likely scenario is that future volcanic activity will be limited to smaller, localized eruptions or hydrothermal explosions. While the threat of a supereruption looms in the public imagination, Yellowstone's true danger lies in its unpredictability. Even minor eruptions or hydrothermal blasts could cause significant damage to surrounding areas. For now, Yellowstone's geysers and geothermal features continue to provide a mesmerizing yet sobering glimpse into the immense forces simmering beneath the Earth's crust. Yellowstone's supervolcano is a reminder that the most powerful geological threats are often the least visible. As monitoring technology advances, scientists hope to gain a clearer understanding of when and how this sleeping giant might awaken, whether in centuries or millennia to come. The underwater volcanoes, hidden giants of the Pacific. Beneath the vast, rolling expanse of the Pacific Ocean lies a chain of volcanic giants that few ever see, the underwater volcanoes of the Pacific Ring of Fire. This horseshoe-shaped region stretches for over 40,000 kilometers, tracing the edges of the Pacific Ocean, and is home to more than 75% of the world's active and dormant volcanoes. Most of these volcanoes are hidden beneath the waves, their eruptions masked by the ocean's surface. Yet, their explosive power is no less significant than that of their land-based counterparts. The submarine eruptions that occur along the Ring of Fire often go unnoticed until they trigger tsunamis, seismic tremors, or lead to the birth of new islands. Unlike terrestrial volcanoes, underwater eruptions can rapidly cool lava, causing it to harden into pillar-like formations. Over time, these formations accumulate, rising above the water and creating entirely new landmasses. The islands of Japan, Tonga, and the Philippines owe much of their existence to this relentless volcanic activity. One of the most fascinating aspects of underwater volcanoes is their ability to generate mysterious seismic activity. Unlike earthquakes caused by shifting tectonic plates, volcanic tremors beneath the ocean floor can signal magma movement long before an eruption occurs. These tremors are crucial for scientists attempting to predict submarine eruptions, yet they are often difficult to detect due to the remoteness and depth of many underwater volcanoes. In January 2022, the world witnessed firsthand the power of underwater volcanic activity when the Hunga Tonga Hunga Hapai volcano erupted with unprecedented force. Located just north of Tonga in the South Pacific, this submarine volcano erupted so explosively that it sent ash plumes over 58 kilometers into the atmosphere, triggering a tsunami that impacted countries as far away as Peru and Japan. The eruption produced shockwaves that circled the globe multiple times, making it the largest volcanic explosion of the 21st century. What made the Tonga eruption so alarming was the lack of warning signs. Scientists have been monitoring the volcano for years, yet the scale and intensity of the blast caught the global scientific community off guard. The eruption released more energy than the most powerful nuclear tests, and the resulting ash cloud disrupted satellite communications and air travel across the Pacific. Despite advances in monitoring technology, the depth and unpredictability of underwater volcanoes continue to challenge volcanologists. The formation of new land after the eruption was another extraordinary phenomenon. While the explosive force obliterated parts of the original volcanic cone, new deposits of ash and lava began to reshape the seafloor, hinting at the potential emergence of a new island in the future. This cyclical process of destruction and creation is a defining characteristic of underwater volcanoes, underscoring their role in shaping the Pacific's ever-changing geography. The underwater volcanoes of the Pacific Ring of Fire remain a hidden threat to coastal communities and global infrastructure. As monitoring systems improve, scientists hope to gain a better understanding of these submerged giants, but for now, they continue to remind us that some of the Earth's most powerful forces are concealed beneath the ocean's surface, waiting to awaken without warning. Unexplained volcanic phenomena. Volcanoes that don't erupt, the silent giants across the globe. Countless volcanoes appear to be in deep slumber. Some, like Mount Fuji in Japan, stand as tranquil icons of nature, drawing tourists to admire their beauty. Yet beneath their quiet exteriors lies a hidden world of subtle activity. Though Mount Fuji's last major eruption occurred in 1707, it continues to emit faint plumes of gas and sulfur, hinting that its volcanic heart still beats softly beneath the surface. These silent volcanoes present a paradox. While they exhibit no explosive eruptions, seismic sensors often detect low-frequency tremors, vibrations caused by magma shifting deep underground. This movement rarely breaches the surface, but it's a sign that molten rock is active below, pressurizing chambers that may one day erupt. In some cases, gas emissions from summit craters fluctuate, reinforcing the possibility that these sleeping giants are more restless than they appear. Mount Hood in Oregon is another example. Although it hasn't erupted in over 200 years, steam vents and minor earthquakes persist. This kind of hidden activity raises questions for volcanologists. How long can a volcano remain dormant before reawakening? Could these quiet emissions serve as early warning signals for future eruptions, or are they simply part of a volcano's natural breathing process? Silent volcanoes are unpredictable because they lack the regular eruption patterns of more active systems. Instead, they may harbor vast reservoirs of viscous magma, gradually increasing internal pressure over centuries. The longer a volcano remains inactive, the greater the potential for a violent eruption when it finally awakens. The mystery of these quiet giants highlights the delicate balance beneath the Earth's crust, an equilibrium that could shift at any time. Mysterious sounds and lights, nature's warning signals before some of history's most devastating eruptions, witnesses have reported strange phenomena, unearthly noises, rumblings, and mysterious lights illuminating the sky. These reports often go unrecorded by scientific instruments, yet they appear repeatedly in historical accounts. In the days leading up to the eruption of Mount St. Helens in 1980, residents described low, echoing booms reverberating through the valleys. Similar accounts emerged before the eruption of Krakatoa in 1883. These sounds, known as harmonic tremors, are thought to be caused by magma rising through narrow fissures, producing vibrations akin to the deep notes of a pipe organ. Even more mysterious are the lights that dance across the sky during eruptions. Known as volcanic lightning, these electric discharges occur when ash particles collide and generate static electricity. Blue, purple, and white flashes illuminate the volcanic plume, creating an otherworldly spectacle. The eruption of Eyjafjallajökull in Iceland in 2010 produced dazzling lightning storms that were visible for miles, adding to the drama of the event. However, not all volcanic lights are associated with eruptions. In some cases, strange glowing auras have been spotted above dormant volcanoes, further deepening the mystery. Could these be early indicators of rising magma, or are they purely atmospheric phenomena unrelated to volcanic activity? While scientists continue to investigate, such unexplained sights fuel the enduring belief that volcanoes possess supernatural qualities that defy modern understanding. Volcanic winter, when eruptions darken the world, few natural disasters rival the global impact of volcanic winter, a phenomenon triggered by massive eruptions that release vast quantities of ash and sulfur dioxide into the upper atmosphere. These particles reflect sunlight away from the Earth, causing dramatic drops in temperature and disrupting weather patterns worldwide. One of the most famous examples is the eruption of Mount Tambora in 1815. The resulting ash cloud circled the globe, plunging temperatures by several degrees and leading to the year without a summer, in 1816. Crops failed, livestock died, and widespread famine gripped Europe and North America. In China, unseasonable snowstorms devastated rice fields, underscoring how a single volcanic event could ripple across continents. Volcanic winter isn't just a modern phenomenon. Geological evidence suggests that mass extinctions in Earth's distant past were fueled by volcanic activity. The Permian Triassic extinction event, known as the Great Dying, wiped out over 90% of marine species and is believed to have been triggered by massive volcanic eruptions in Siberia. These eruptions released enough toxic gas and ash to choke the planet, initiating a prolonged period of cooling and acid rain. Ancient civilizations may have also fallen victim to volcanic winter. In the 6th century AD, a mysterious period of global cooling devastated agricultural societies. Modern studies point to volcanic eruptions in Central America as the likely culprit. The Maya civilization, whose population declined sharply during this period, may have faced prolonged drought and famine due to disrupted weather cycles. The fear of volcanic winter remains relevant today. A supereruption from Yellowstone or another major caldera could potentially plunge the world into a modern-day volcanic winter, causing untold damage to global infrastructure and economies. Understanding this phenomenon is crucial not only for historical insight but for preparing future generations against one of nature's most far-reaching threats. Hidden worlds beneath volcanoes, lava tubes and underground chambers. Nature's hidden tunnels beneath the surface of active and dormant volcanoes lies a labyrinth of lava tubes and underground chambers, carved by molten rock as it flows beneath the Earth's crust. These vast, hollow tunnels are formed when the outer layer of a lava flow cools and solidifies, while the molten interior continues to move, leaving behind an empty passageway. Over time, these tubes can stretch for miles, creating complex networks that snake through volcanic landscapes. One of the most famous examples of lava tubes is found in Hawaii Volcanoes National Park, where tubes formed by eruptions from Mauna Loa and Kilauea create subterranean pathways large enough to walk through. These tunnels provide insight into how lava flows behave and cool, offering glimpses into the volcanic processes that shape islands and continents. The discovery of lava tubes beneath volcanoes raises an intriguing question: could these underground networks harbor unknown ecosystems? Despite the intense heat and sulfurous gases that permeate volcanic environments, life often finds a way to survive. In some lava tubes, researchers have discovered microbial colonies thriving in the mineral-rich walls, suggesting that these hidden spaces could support unique life forms adapted to extreme conditions. Some scientists speculate that studying lava tubes on Earth could provide clues to what lies beneath the surface of Mars or the Moon, where ancient volcanic activity may have left behind similar subterranean structures. Lava tubes also serve as potential refuges for wildlife during eruptions. Animals have been observed seeking shelter within these tunnels, where temperatures remain relatively stable even as surface conditions become hostile. This ability to sustain life, even in the aftermath of volcanic eruptions, underscores the resilience of nature and the hidden potential of volcanic landscapes. Magmatic chambers. The molten heart of a volcano. Deeper beneath the surface lies the magmatic chamber, a massive reservoir of molten rock that serves as the powerhouse of volcanic eruptions. These chambers, often located kilometers below ground, are filled with pressurized magma that slowly accumulates over centuries. When the pressure becomes too great, the chamber fractures, sending magma surging toward the surface in an eruption. Magmatic chambers are constantly evolving, expanding as new magma flows in from the mantle. In some cases, these reservoirs grow so large that they can deform the ground above, creating noticeable bulges that warn of impending eruptions. Scientists closely monitor these changes using satellite imagery and ground-based measurements, tracking even the slightest shifts in elevation around active volcanoes. One of the biggest mysteries surrounding magmatic chambers is how they interact with tectonic plates. As magma pools beneath a volcano, it can exert immense pressure on surrounding rock, potentially triggering earthquakes or causing the plates to shift. This dynamic relationship between molten rock and the Earth's crust plays a critical role in shaping the landscapes of volcanic regions. There is also the question of whether magmatic chambers can collapse. In rare cases, the roof of a chamber may implode after an eruption, forming a caldera, a large, crater-like depression. This phenomenon occurred at Yellowstone, where repeated supereruptions have left behind vast calderas that hint at the immense reservoirs of magma lurking below. Understanding the behavior of magmatic chambers is key to predicting future volcanic activity. By studying these molten reservoirs, scientists hope to unravel the secrets of volcanic life cycles and develop more accurate models for forecasting eruptions. The link between volcanoes and earthquakes, a dangerous connection. Volcanoes and earthquakes are often seen as distinct geological events, but the two are deeply intertwined. Volcanic activity frequently triggers seismic events, as the movement of magma disturbs the surrounding crust. In some cases, volcanic eruptions are preceded by swarms of small earthquakes, foreshocks that signal magma is rising through the Earth's crust. This pattern was observed before the eruption of Mount St. Helens in 1980, where a series of tremors culminated in a massive lateral blast that reshaped the volcano's summit. The connection between volcanoes and earthquakes extends beyond individual eruptions. Some of the world's most active seismic zones overlap with volcanic hotspots, particularly along subduction zones like the Pacific Ring of Fire. Here, tectonic plates collide and sink beneath one another, generating both volcanic eruptions and large-magnitude earthquakes. This dual threat makes regions like Japan, Indonesia, and Chile highly susceptible to natural disasters. One of the most compelling questions is whether volcanoes can act as warning signals for larger earthquakes. Some scientists theorize that the buildup of magma beneath a volcano can place stress on nearby faults, increasing the likelihood of earthquakes. In rare cases, volcanic activity has been linked to megathrust earthquakes, such as the 1960 Valdivia earthquake in Chile, the most powerful earthquake ever recorded. However, not all earthquakes near volcanoes lead to eruptions. Sometimes, the seismic activity reflects the shifting of tectonic plates rather than the movement of magma. This complexity makes it challenging to determine whether a volcano-related earthquake will culminate in an eruption or remain a geological curiosity. Despite the challenges, advancements in seismic monitoring have improved scientists' ability to detect early warning signs. Networks of sensors placed around volcanoes can record the faintest tremors, providing critical data that helps volcanologists assess whether magma is on the move. By analyzing these patterns, researchers can better understand the intricate dance between volcanoes and earthquakes, ultimately enhancing our ability to forecast and mitigate the risks posed by these interconnected forces of nature. The role of volcanoes in shaping Earth-land formation. The architects of continents and islands. Volcanoes are the Earth's natural architects, continually building and reshaping the land we inhabit. From towering mountain ranges to isolated islands, much of the planet's surface owes its existence to volcanic activity. Nowhere is this more evident than in the Pacific Ocean, where volcanic hotspots have given rise to the Hawaiian Islands. The archipelago, stretching over 1,500 kilometers, was born from magma rising from a hotspot deep beneath the Pacific Plate. As the plate slowly drifts, new islands emerge while older ones erode, demonstrating how volcanic activity can literally create land out of the sea. Iceland offers another striking example of volcano-driven land formation. Positioned atop the mid-Atlantic ridge, Iceland is one of the few places on Earth where volcanic activity occurs directly along a tectonic boundary. As the North American and Eurasian plates diverge, magma wells up to fill the gap, gradually expanding the island's surface area. The island's dramatic landscapes, defined by lava fields, geysers, and glacial rivers, are shaped by the ongoing interplay between fire and ice. Volcanic eruptions are not just confined to isolated islands, they play a critical role in the formation of continental landmasses. During Earth's early history, repeated volcanic eruptions released vast quantities of basaltic lava, which cooled and solidified to form the foundation of continents. Even today, regions like the East African Rift Valley continue to experience volcanic activity that slowly alters the shape of the land. Over time, new volcanoes emerge, while old ones erode into fertile plains, enriching the soil and sustaining ecosystems. Volcanoes also contribute to land regeneration. After the eruption of Mount St. Helens in 1980, more than 600 square kilometers of forest were obliterated. Yet within decades, plant life began to return, and the landscape slowly healed. This process of destruction and renewal exemplifies the paradoxical role of volcanoes. They are both creators and destroyers of land. Atmospheric impact. Volcanoes and the air we breathe. While the physical landforms created by volcanoes are the most visible aspect of their activity, their impact extends far beyond the surface. Volcanic eruptions release a cocktail of gases and particles into the atmosphere, influencing everything from local weather patterns to global climates. Sulfur dioxide, carbon dioxide, and water vapor are among the most significant gases emitted during eruptions, and their effects can linger long after the lava cools. When sulfur dioxide combines with water vapor in the upper atmosphere, it forms sulfate aerosols, which reflect sunlight and cause global cooling. This phenomenon was observed after the eruption of Mount Tambora in 1991, which lowered average global temperatures by nearly 0.6 degrees Celsius for 2 years. Similar effects were recorded following the 1815 eruption of Mount Tambora, which triggered the infamous year without a summer and led to widespread crop failures. However, the atmospheric impact of volcanoes isn't purely destructive. The carbon dioxide released during eruptions contributes to the carbon cycle, playing a vital role in maintaining Earth's temperature over geological timescales. Without volcanic emissions, the planet could eventually enter a state of icehouse Earth, where global cooling becomes irreversible. Volcanoes also enrich the atmosphere with essential minerals that promote life. The ash ejected during eruptions contains nutrients like potassium, phosphorus, and magnesium, which fertilize the soil and enhance agricultural productivity. Regions surrounding active volcanoes often boast some of the most fertile farmland in the world, sustaining dense populations despite the inherent risks. The volcanic plains of Java, for instance, support millions of people due to the richness of the soil, even as nearby Mount Merapi continues to erupt periodically. In this way, volcanoes play a dual role in shaping the atmosphere, regulating temperatures, providing nutrients, and influencing long-term climate cycles. Life after eruption, nature's rebirth on volcanic landscapes. In the aftermath of a volcanic eruption, the landscape is often left barren and desolate, covered by layers of ash and cooled lava. Yet this seemingly lifeless terrain holds the seeds of new beginnings. Nature's ability to reclaim volcanic landscapes is nothing short of remarkable, as plants, animals, and ecosystems gradually return to rebuild what was lost. One of the most compelling examples of this regeneration can be seen at Mount St. Helens. In the years following its eruption, scientists observed the return of plant species like fireweed and lupine, which were among the first to colonize the ash-covered slopes. These hardy plants laid the groundwork for more complex ecosystems, attracting insects, birds, and eventually larger mammals. The area around Mount St. Helens now stands as a testament to the resilience of life, with dense forests reclaiming the scarred landscape. The volcanic landscapes of Hawaii tell a similar story. After each eruption, lava flows obliterate existing vegetation, leaving behind black, hardened surfaces. Over time, small ferns and mosses take root in the cracks, breaking down the volcanic rock and creating pockets of soil. This slow but steady process allows more robust plant species to establish themselves, ultimately transforming the lava fields into thriving rainforests. Volcanoes also play a crucial role in creating biodiversity hotspots. Isolated volcanic islands, like the Galapagos or the Azores, provide unique environments where species evolve in isolation. The volcanic origins of these islands give rise to ecosystems that cannot be found anywhere else on Earth, contributing to the planet's rich biological diversity. Additionally, volcanic environments are often home to rare and specialized species that thrive in extreme conditions. Microbial life has been found in the steaming fumaroles of Mount Etna and within the acidic crater lakes of Mount Rinjani, demonstrating that life can flourish even in the most hostile settings. The cycle of life and death on volcanic landscapes underscores the profound relationship between geology and biology. While eruptions may bring devastation, they also pave the way for ecological renewal and evolution. Volcanoes serve as reminders that Earth is a planet in constant flux, shaped by forces that destroy and rebuild, giving rise to new land, life, and possibilities. Controversial theories and unsolved volcanic mysteries. Supervolcanoes and mass extinction. Did volcanoes kill the dinosaurs? For decades, scientists have debated the events that led to the extinction of the dinosaurs 66 million years ago. While the prevailing theory points to a massive asteroid impact that left the Chicxulub crater in Mexico, another compelling argument centers around volcanic activity, specifically, the colossal eruptions that formed the Deccan Traps in present-day India. These eruptions, which spanned tens of thousands of years, released vast amounts of lava, ash, and toxic gases into the atmosphere, triggering catastrophic environmental changes. The Deccan Traps are believed to have spewed over 1.3 million cubic kilometers of lava, covering an area larger than Texas. The gases released during this volcanic event likely acidified oceans, darkened skies, and plunged the planet into a state of volcanic winter. This chain of events could have devastated ecosystems, disrupting food chains and contributing to the mass extinction that wiped out nearly 75% of life on Earth. Some scientists argue that volcanic activity was the primary driver of extinction, while others suggest that the asteroid impact may have intensified the effects of ongoing eruptions. The combination of both disasters could explain the rapid collapse of dinosaur populations. However, the precise role of volcanoes in this extinction event remains an open question, as geological records continue to be analyzed. Adding to the mystery, evidence from other extinction events points to similar volcanic activity as a catalyst for global upheaval. The Permian Triassic extinction, which occurred 252 million years ago, is linked to volcanic eruptions in Siberia that wiped out over 90% of marine species. These massive lava flows, known as the Siberian Traps, mirror the scale and impact of the Deccan Traps. The possibility that supervolcanoes could trigger global extinction events raises concerns about future eruptions. While humanity has yet to witness a super-eruption of this magnitude, the geological record serves as a stark reminder that the Earth's internal forces can shape the fate of life itself. Unknown volcanoes, hidden threats beneath the ocean. The Earth's surface is dotted with over 1,500 active volcanoes, but beneath the oceans lie countless undiscovered volcanic systems. The vast majority of volcanic activity occurs underwater, hidden from view along mid-ocean ridges and subduction zones. Scientists estimate that over 80% of the planet's volcanic eruptions take place beneath the sea, yet only a fraction of these have been mapped or studied in detail. One of the greatest mysteries is whether undiscovered supervolcanoes exist beneath the ocean floor. These colossal systems could potentially trigger devastating eruptions capable of altering global climates and sea levels. Recent advancements in sonar mapping and satellite technology have revealed underwater calderas, depressions in the seafloor formed by massive eruptions, that hint at the presence of supervolcanic activity. In 2013, researchers discovered a massive underwater volcano known as Tamu Massif in the Pacific Ocean. Spanning an area the size of New Mexico, Tamu Massif is now considered one of the largest volcanoes on Earth. Its existence went unnoticed for millions of years, raising the question of how many more hidden giants lie beneath the ocean's surface. The Tonga eruption in 2022 demonstrated the destructive potential of submarine volcanoes. The explosion of Hunga Tonga Hunga Hapai not only triggered a massive tsunami but also produced shockwaves that circled the globe. This eruption served as a wake-up call for volcanologists, highlighting the need for greater surveillance of underwater volcanic systems. As technology advances, scientists are developing new tools to detect volcanic activity beneath the ocean, from autonomous drones to deep-sea monitoring networks. These innovations are slowly unraveling the secrets of Earth's hidden volcanoes, but the sheer scale of the oceans ensures that many mysteries remain unsolved. The debate on eruption predictions: can we see it coming? Predicting volcanic eruptions is one of the most challenging tasks in modern geology. While scientists have made significant strides in monitoring seismic activity, ground deformation, and gas emissions, accurately forecasting when and how a volcano will erupt remains frustratingly elusive. Some volcanoes, like Mount St. Helens, provide ample warning signs, weeks or even months of small earthquakes and steam emissions that signal magma is rising. In other cases, volcanoes erupt with little to no warning, leaving scientists scrambling to explain why the usual indicators fail. One of the biggest hurdles is that every volcano behaves differently. While some exhibit predictable patterns, others defy logic, erupting sporadically even after years of dormancy. Iceland's Eyjafjallajökull, which erupted in 2010, had shown only minor signs of unrest, yet its eruption caused widespread disruption to air travel across Europe. Some researchers argue that volcanic eruptions are inherently unpredictable due to the complexity of magma systems beneath the surface. Magma may accumulate in irregular chambers, moving unpredictably through networks of cracks and fissures. Even if sensors detect magma rising, the exact moment when the system will breach the surface can be impossible to pinpoint. Others believe that better technology and data analysis could revolutionize eruption forecasting. By using artificial intelligence and machine learning, volcanologists are analyzing vast datasets to identify subtle patterns that might precede eruptions. Early results from machine learning algorithms suggest that volcanic activity may follow hidden cycles that are difficult for humans to detect but can be revealed through advanced computational models. Despite these advancements, many in the scientific community remain cautious. Some believe that over-reliance on technology could lead to complacency, as no model can account for the full complexity of volcanic systems. Instead, volcanologists emphasize the importance of ongoing fieldwork and observation, recognizing that even the most sophisticated sensors cannot replace the insights gained by studying volcanoes up close. The debate over eruption predictions continues to shape the future of volcanology. While the dream of accurately forecasting eruptions remains just out of reach, each discovery brings humanity closer to understanding the volatile forces that lie beneath the Earth's crust. Until then, volcanoes will continue to remind us of their unpredictable and untamable nature. The future of volcano monitoring and exploration cutting-edge technology, a new era of volcano studies. Volcano monitoring has entered a revolutionary phase, driven by advancements in drones, satellites, and artificial intelligence. These technologies are transforming the way scientists observe, predict, and respond to volcanic activity, offering unprecedented insights into the hidden processes beneath the Earth's surface. Drones have become an essential tool in volcano exploration, allowing researchers to gather data from dangerous and inaccessible areas. Equipped with cameras, gas sensors, and thermal imaging systems, drones can fly directly over active craters, capturing real-time footage and detecting changes in temperature and gas emissions. This technology was instrumental in monitoring eruptions at Kilauea in Hawaii, where drones mapped lava flows and provided critical information that helped direct evacuation efforts. Satellites, too, are playing a pivotal role. Programs like NASA's Landsat and the European Space Agency's Copernicus provide continuous, high-resolution imaging of volcanic regions around the world. Satellites can track ground deformation, an early indicator that magma is building beneath a volcano. By comparing satellite images over time, scientists can detect even the slightest bulge or shift in the landscape, offering valuable clues about impending eruptions. Artificial intelligence is emerging as a game-changer in volcanic prediction. By analyzing seismic data, gas emissions, and thermal patterns, AI algorithms can identify trends that might escape human observation. AI models are currently being tested in areas like Japan and Iceland, where dense networks of sensors generate massive amounts of data. These models are already showing promise in forecasting smaller eruptions, and researchers hope they will one day predict larger, more destructive events with greater accuracy. While technology has dramatically improved monitoring capabilities, it also presents challenges. Drones can be damaged by volcanic ash, and satellite coverage is limited in regions with persistent cloud cover. Nonetheless, the combination of drones, satellites, and AI is creating a multi-layered monitoring system that brings scientists closer than ever to understanding the behavior of volcanoes. Predicting the next big eruption, lessons from the past. The ability to predict volcanic eruptions has long been a goal for volcanologists, but despite technological advancements, the task remains daunting. Some eruptions provide ample warning, while others occur with little or no forewarning, highlighting the unpredictable nature of volcanic systems. One of the most notable success stories in eruption prediction is the 1980 eruption of Mount St. Helens in Washington. In the months leading up to the explosion, scientists detected earthquake swarms and ground deformation, prompting them to issue warnings and evacuate surrounding areas. Though the eruption claimed 57 lives, the death toll would have been far higher without these early warnings. Similarly, the 1991 eruption of Mount Pinatubo in the Philippines stands as a triumph of scientific forecasting. Volcanologists observed increasing seismic activity and rising gas emissions, leading to the evacuation of more than 60,000 people. When Pinatubo erupted, it became the second largest eruption of the 20th century, but the successful evacuation efforts saved thousands of lives. However, not all eruptions are so cooperative. In 2019, the eruption of Whakaari, White Island, in New Zealand took scientists by surprise. Although the volcano had shown minor signs of unrest, the sudden explosion claimed 22 lives. This tragedy underscored the limitations of current prediction models, particularly for volcanoes with complex or poorly understood magma systems. The challenge lies in the variability between volcanoes. While some follow predictable patterns, others remain dormant for centuries, only to erupt without warning. Scientists continue to refine their models, but the inherent complexity of volcanic processes makes perfect prediction an elusive goal. Volcanic energy, tapping into Earth's power. Volcanoes are not just destructive forces, they are also sources of immense energy. Geothermal energy, which harnesses heat from beneath the Earth's crust, is already being used in volcanic regions to power homes and industries. Countries like Iceland, New Zealand, and the Philippines rely heavily on geothermal energy, tapping into underground reservoirs of steam and hot water to generate electricity. Iceland's geothermal plants supply nearly 90% of the country's heating and 30% of its electricity, showcasing the potential of volcanic energy to drive sustainable development. The geothermal fields surrounding Krafla volcano produce enough electricity to power tens of thousands of homes, demonstrating how volcanic activity can be transformed into a renewable resource. The potential for expanding geothermal energy is vast, but the process is not without risks. Drilling into volcanic areas can sometimes trigger small earthquakes or disturb underlying magma chambers. Additionally, not all volcanic regions have easily accessible geothermal reservoirs. Scientists are exploring advanced drilling techniques that could allow geothermal plants to tap into deeper, hotter sources of energy, potentially unlocking the full power of volcanic systems. With the increasing demand for renewable energy, geothermal power is likely to play a growing role in global efforts to combat climate change. Volcanoes, once seen solely as threats, may become cornerstones of sustainable energy in the decades to come. Preparing for the next global eruption, early warning and evacuation. The question is not if another major volcanic eruption will occur, but when. Governments and scientific organizations around the world are developing early warning systems to mitigate the potential devastation of future eruptions. These systems rely on a combination of seismic monitoring, satellite surveillance, and ground-based sensors to detect early signs of volcanic unrest. In Japan, the Japan Meteorological Agency, JMA, operates one of the most advanced volcanic monitoring networks in the world. More than 110 active volcanoes are under constant surveillance, and the agency regularly issues alerts to nearby communities. Similarly, Italy's Mount Vesuvius is closely monitored by the Vesuvius Observatory, where evacuation plans are in place for the millions of residents living in the volcano's shadow. One of the most successful evacuation efforts occurred in 2010, when Eyjafjallajökull erupted in Iceland. Although the eruption disrupted global air travel, the local population had been evacuated in advance, resulting in no loss of life. This case highlights the importance of preparation and public awareness in reducing the impact of volcanic disasters. Despite these successes, many volcanic regions remain vulnerable. Developing countries with limited resources often lack the infrastructure needed for effective monitoring and evacuation. International organizations, such as the Global Volcano Model, GVM, are working to address this disparity by providing funding and technology to high-risk areas. The future of volcano monitoring depends not only on technological innovation but also on global collaboration. As scientists continue to study and unlock the secrets of volcanic activity, the hope is that communities around the world will be better prepared to face the challenges that lie ahead. As we journey through the hidden world of volcanoes, it becomes clear that these geological giants are more than mere forces of destruction. They are architects of continents, shapers of ecosystems, and harbingers of both life and devastation. From the towering peaks of Mount Tambora and Krakatoa to the underwater calderas lurking beneath the Pacific Ring of Fire, volcanoes continue to captivate and mystify humanity. Each eruption leaves behind more than just ash and lava. It leaves clues, fragments of the Earth's inner workings that scientists are still struggling to piece together. The largest eruptions in recorded history, like Tambora's catastrophic explosion in 1815, serve as stark reminders of the sheer scale of volcanic power. Tambora's eruption altered the global climate, plunging the world into the infamous year without a summer. Similarly, the eruption of Krakatoa in 1883 produced a sound so loud it echoed across continents, while tsunamis reshaped coastlines and claimed tens of thousands of lives. These events not only demonstrate the destructive capabilities of volcanoes but also highlight the interconnectedness between volcanic activity and the broader environment. Beneath the Earth's surface, hidden magmatic chambers and lava tubes reveal the unseen forces driving these eruptions. Vast reservoirs of molten rock expand and shift over time, occasionally breaching the surface in spectacular fashion. The Yellowstone supervolcano, for example, lies dormant beneath North America, its last eruption occurring over 600,000 years ago. While Yellowstone may seem peaceful today, the presence of its massive caldera and the geothermal activity bubbling throughout the park serve as quiet indicators of the volatile forces that lie in wait. The mysteries surrounding volcanic lightning, harmonic tremors, and unexplained noises add another layer to our understanding of volcanoes. These phenomena, though observed for centuries, remain partially unexplained, fueling speculation and continued research. Could these strange lights and sounds serve as natural warning signals, or are they simply byproducts of immense geological processes unfolding beneath the crust? Advancements in technology and monitoring systems have transformed the way we study volcanoes. Drones now soar above active craters, capturing real-time data, while satellites track subtle ground deformations from space. Artificial intelligence is revolutionizing eruption prediction, analyzing seismic activity, and gas emissions to identify patterns that might escape the human eye. Despite these breakthroughs, eruption prediction remains an imperfect science. Some volcanoes, like Whakaari in New Zealand, erupt with little to no warning, leaving communities vulnerable and reminding scientists of the challenges that still lie ahead. Volcanoes are not just agents of destruction, they are also potential sources of renewable energy. Geothermal plants harness the immense heat beneath the surface, generating electricity and providing sustainable power to millions of people. Iceland stands as a prime example, where volcanic energy powers nearly one-third of the nation's electricity grid. As the world seeks cleaner energy solutions, volcanic energy may emerge as a cornerstone of future sustainability efforts. For now, the best we can do is continue to explore, monitor, and respect these powerful natural forces.